Good evening. I'm Doug Draper, President of Cincinnati Radiation Society, and I'd like to introduce Catesby Mallard from the University of Alabama, Birmingham, who's going to be giving our talk tonight. Catesby's finishing her master's degree at the University of Alabama in Birmingham. For those of you that aren't really familiar with that program, it has become one of the nationally recognized programs in health physics in the country. Their chairman of the department, Dr. Emily Caffrey, is now by my standards, I would consider her a youngster, but she's become widely recognized in the health physics community, and she has put together a terrific program at UAB, and it draws a lot of very talented individuals to participate. Catesby is one of them, and I'm expecting that in the future we will see Catesby become as equally as recognized as her mentor. At this time, I'd like to turn the talk over to Catesby, who's going to give us a talk on her on a program that she worked on for her master's.
Thank you, Doug, for that great introduction. If you guys didn't catch it, my name is Catesby Mallard. Tonight, I'm going to be presenting part of my master's thesis on phosphogypsum-based road materials and whether or not their implementation in certain areas of the United States is going to be both safe and practical in the short and long term. And before I get started, I just wanted to preface by saying I'm not going to be able to cover everything that I included in my master's thesis or that I even wanted to cover in this presentation just due to time constraints. But I have a ton of additional slides at the end, so if you do have any questions, please keep them in mind. I'll be happy to take them once we're done. But to go ahead and kick us off, I'm just going to give us an overview of what phosphogypsum is and how it's produced, starting with the raw material that phosphogypsum originates from, which is phosphate rock. So the phosphate rock mining industry is about the 5th largest mining industry in the US, and historically it's been responsible for the production of about 32 million tons of phosphate rock every single year on average from about 1994 to 2022, valued at about $1.6 billion every single year. The US alone has been responsible for about 18% of all global output of phosphate rock. And the reason why this industry is so massive is because phosphate rock is the only significant source of phosphorus in the world. And given the essential role that phosphorus plays in plant life and nutrition, this means that the phosphate rock mining industry is heavily tied to the agricultural industry and food production. And this has been reflected by the fact that about 90 to 95% of all domestic consumption of phosphate rock in the US has been devoted to the manufacture of wet process phosphate fertilizer since about 2003. But what is wet process phosphate fertilizer? It's just a type of fertilizer that incorporates phosphorus by using phosphoric acid that has been produced using a wet chemical process, also known as just wet phosphoric acid. And in order to create this wet phosphoric acid, phosphate rock is dissolved using sulfuric acid to create a slurry of phosphoric acid and phosphogypsum, where that phosphogypsum is mainly just calcium sulfate dihydrate that has been precipitated out in that slurry in the form of a solid as a result of the reaction of the calcium ions in phosphate rock with the sulfate ions from sulfuric acid. And in order to separate out phosphoric acid from the slurry, phosphogypsum, along with any other solids that's present in that slurry, must be filtered out in order to purify and produce that wet phosphoric acid. However, generating phosphoric acid in this manner produces significant amounts of phosphogypsum. And an incredible disproportion, for about every 1 ton of phosphoric acid that's produced using a wet chemical process, about 5.2 tons of phosphogypsum are going to accompany it, resulting in the production of nearly 46 million tons of phosphogypsum every year in the US and about 300 million tons of phosphogypsum every year worldwide. And one of the reasons why this is somewhat of a problem is because phosphogypsum tends to contain residual acids like hydrofluoric acid, making it a really acidic waste byproduct of this wet phosphoric acid industry. Phosphogypsum is also known to contain many different types of impurities, with sources reporting that phosphogypsum can contain up to or nearly even more than about 50 different types of impurities, some of which include things like trace and heavy metals, which if we take a look at some of these listed on the screen, they include things like arsenic, lead, and cadmium, which have no real known biological essential function and can induce toxicity in humans at relatively low levels, contributing to the particularly hazardous nature of phosphogypsum towards human health. But aside from these trace and heavy metals, phosphogypsum also tends to contain various amounts of oxides, such as quartz, as well as things like ammonia, chlorides, soluble phosphates, and rare earth elements, which has led to some interest in trying to reuse phosphogypsum as a raw material for the recovery of rare earth elements as well. And although these are not all the impurities that can be found in phosphogypsum, these are some of the most common that you see in literature, or at least that I saw when I was performing my literature review to determine the composition of phosphogypsum. However, the concentrations of a lot of these impurities tend to vary significantly based on multiple factors. For example, if we take a look at different samples of phosphogypsum produced in, say, Morocco, the US, and Brazil, and specifically some of those trace and heavy metals, we can see that their concentrations vary significantly, with Morocco containing higher concentrations of chromium, lead, and nickel when compared with phosphogypsum produced in either the US or Brazil. We can see that the US has higher concentrations of arsenic and cadmium when compared with those other countries, and Brazil overall had just lower concentrations of these trace and heavy metals in general, with the exception of lead. And the differences in these concentrations can be attributed to multiple factors, including plant-specific operations, so maybe the type of wet process that's employed, your plant operation efficiency, maybe your disposal method, as well as your production country, as well as phosphate rock-specific properties, so maybe the nature and the quality of your phosphate rock itself, where it was sourced, and how deep it was sourced from the girth. So again, it's important to recognize and know some of these non-radiological constituents in phosphogypsum because they can be hazardous to human health. However, the reason why we care about it as health physicists has to do with that raw material that phosphogypsum originates from, which is phosphate rock. And this is because phosphate rock tends to contain some amount of naturally occurring radioactive material, or NORM, which the EPA defines as any material which may contain primordial radionuclides or radioactive elements as they occur in nature, such as radium, uranium, thorium, or potassium, as well as all of their radioactive decay products that are left undisturbed as a result of human activities. The EPA has reported that in the US, phosphate rock tends to contain anywhere from about 7 to 100 picocuries per gram of uranium, while only about 0.1 to 0.6 picocuries per gram of thorium. And if we go back to that wet chemical process, when that phosphate rock is dissolved using sulfuric acid to create that slurry of phosphoric acid and phosphogypsum, any type of radioactive equilibrium that's present between uranium or thorium, as well as all of their radioactive decay products, is essentially disrupted, resulting in certain radionuclides like radium-226, radium-228, or lead-210 being present in the slurry as more of insoluble phosphates, sulfates, or unreacted monocytes, while other radionuclides like uranium-238 or thorium-232 might be present in the slurry as more of a soluble mobile phase. So what does this mean? This means that when that phosphogypsum is filtered out from the slurry, radionuclides are going to preferentially separate and concentrate either into phosphoric acid or phosphogypsum based on whether or not they're present in that slurry as more of a soluble or insoluble phase. Sources typically report that in the US, about 14% of uranium-238, 30% of thorium-232, and about 80% of radium-226 preferentially separate and concentrate into phosphogypsum during this wet chemical process, and it's specifically because we have taken that naturally occurring radioactive material in phosphate rock and concentrated it into phosphogypsum as a result of human activities that phosphogypsum meets the EPA's definition of technologically enhanced naturally occurring radioactive material, or TNORM, and is classified by the EPA as TNORM. And although I did say that these are the concentrations or the percentages of uranium-238, thorium-232, and radium-226 that we typically see concentrate into phosphogypsum in the US during this wet chemical process, just like some of those non-radiological constituents that we saw earlier, the concentrations of radionuclides and phosphogypsum tend to dramatically vary based on some of those same factors that we discussed earlier on in this presentation. For example, If you take a look at this slide, it depicts some of the radionuclide concentrations of phosphogypsum produced in various countries. And as you can see, phosphogypsum produced in Sweden tends to have higher concentrations of uranium-238 than any other country on this figure. Spain had higher concentrations of thorium-230, but most notably, Florida had significantly higher concentrations of radium-226, lead-210, and polonium-210 than any other country in this figure. And the T-norm present in phosphogypsum alone and its dramatic variation isn't necessarily what caused the EPA to begin regulating phosphogypsum in the US in the first place. Rather, those elevated concentrations of radium-226 in particular. And at this point, you might be wondering, well, why radium-226? What's so special about it? Well, as those elevated concentrations of radium-226 decay in phosphogypsum, they lead to the subsequent emission of elevated levels of radon-222, or just radon, which is a colorless, odorless gas that tends to exist in the atmosphere at levels which typically don't pose a threat to human health. However, it is known that elevated levels of radon can increase the risk for lung cancer. And it's these elevated emissions of radon and their associated risk or increased risk in lung cancer are what caused the EPA to begin regulating phosphogypsum in the first place in 1989 under 40 CFR Part 61 under the National Emission Standards for Hazardous Air Pollutants as authorized by the Clean Air Act. Currently, there are only 2 approved uses for phosphogypsum in the US by the EPA, either in the agricultural industry, where that phosphogypsum must contain less than 10 picocuries per gram of radium-226, or for indoor research and development. All other alternative uses of phosphogypsum must receive prior approval from the EPA by submitting a petition to the EPA requesting that new alternative use of phosphogypsum and proving that it is at least as protective to human health as the current methods of disposal in both the short and long term, with those current methods of disposal being storing phosphogypsum in stacks. So stacks are essentially just really large waste piles of phosphogypsum that require really large areas of land. They tend to be located on privately owned land away from the general public, again, in order to protect the general public from those elevated emissions of radon, with the EPA reporting that the average radon flux from phosphogypsum stacks in the US is around 6.8 picocuries per meter squared per second, but it can range up to 340 picocuries per meter squared per second. For reference, the natural average radon soil flux in south central Florida has been reported to range anywhere from about 0.4 to 1.26 picocuries per meter squared per second, so significantly lower than what we can see from some of these phosphogypsum stacks. These stacks are also typically not watertight. They're left completely open to the atmosphere until they're deemed inactive, which just means we're no longer pumping phosphogypsum onto these stacks. And once they're deemed inactive, they're then covered, and the EPA begins requiring that these phosphogypsum stack owners monitor and report that radon flux, limiting it to less than 20 picocuries per meter squared per second, while covered and inactive. And before we move on, if you take a look at the figure in the upper right corner of the slide, you might notice that it almost looks like there are little lakes or beaches on top of these stacks, and that's intentional, that's by design. As that phosphogypsum slurry is pumped onto these stacks over time and they grow in size, the solid portion of the phosphogypsum is going to settle to the bottom of these stacks, and then they'll also intentionally dredge the solid portion up the sides of these stacks in order to create a reservoir of processed wastewater, where they'll either recycle that processed wastewater back into that wet phosphoric acid production plant, or they'll just let it evaporate off over time. So ultimately, what has this led to? Well, with the EPA regulating the use and disposal of phosphogypsum in the US to disposal and storage in stacks, this has led to the accumulation of nearly 1.7 billion tons of phosphogypsum across the country in about 13 different states in about 70 different identified stacks. And although there's not necessarily much publicly available information about how much phosphogypsum is stored in maybe each stack or in each state in particular, we do know a significant amount of information about the phosphogypsum produced and stored in Florida. We know that Florida is responsible for about 75% of all phosphate rock mining in the US. We know that they're responsible for producing 30 to 40 million tons of phosphogypsum out of the 46 million tons that the US produces every single year. And we know that Florida is responsible for disproportionately storing the majority of the phosphogypsum in the country, holding one of the 1.7 billion tons of phosphogypsum currently stored in the US. And when compared with that annual production rate of about 46 million tons of phosphogypsum per year, the US really only uses about 240,000 tons of phosphogypsum annually for agricultural purposes. And this limited reuse is reflected worldwide, with only about 15% of the phosphogypsum that's produced recycled every single year across the world, mainly, again, due to its toxic and radioactive properties. The rest of that phosphogypsum is either disposed of in stacks or it's discharged untreated into the ocean. And although we won't be talking about discharge into the ocean any further because it's prohibited in the US, it is a type of disposal method that's worth knowing. And at this point, you might be wondering, well, when compared with options like discharging it untreated into the ocean, why then do we really care about how much phosphogypsum we're recycling or storing in stacks? And this is because those current methods of disposal in stacks can have negative environmental impacts, especially if they're improperly managed. Because these stacks are left open to the atmosphere over time, other hazardous gases alongside radon, as that phosphogypsum stack weathers and erodes, are going to be released, as well as particulate matter and nanoparticles, which can contain and potentially disperse radioactive and toxic elements. Additionally, multiple sources have reported local groundwater and soil pollution as a result of heavy metal and radionuclide leaching from phosphogypsum stacks into the local environment. And finally, phosphogypsum stacks in the US have experienced a long history of sinkholes, structural failures, and overflowing of processed wastewater into local rivers and the environments as a result of inclement weather, resulting in the accidental release of hundreds of millions of gallons of untreated processed wastewater into local environments, all of which can have negative impacts on the environment, animal, and human health. But in addition to these things, these stacks are also absolutely massive in size. They can range anywhere from about 5 to 800 acres in surface size and about anywhere from 3 to 60 meters in height. And although phosphogypsum isn't federally regulated under the Resource Conservation and Recovery Act, or RCRA brings up a good point about needlessly polluting land in order to store waste. With urban development and population growth only expected to rise in the coming century, do we really want to perpetually store phosphogypsum in this manner and take up all of this valuable land? Lastly, managing and maintaining phosphogypsum in these stacks is also incredibly costly, with estimated costs from 2020 to 2042 ranging anywhere from about $880 million to nearly $1.3 billion. And with other countries across the world already moving towards the reuse of phosphogypsum as opposed to storing it in stacks, in order for wet phosphoric acid production plants in the US to remain competitive in international markets, the US must also begin to move towards reusing phosphogypsum as well. And one of the ways that we can reuse phosphogypsum, which is the way that we're going to be talking about today, is by reusing phosphogypsum as a road-based material. And it's not a question of can we do this. There's been a ton of research into this field and a ton of different materials that have been identified that can stabilize phosphogypsum enough to where it either meets or even exceeds mechanical and geotechnical properties required for materials used in road construction. In fact, the only petition that is requesting a new alternative use of phosphogypsum that is currently approved by the EPA in the US is a small-scale pilot road study by Mosaic Fertilizer in 2022 in Florida, where they have proposed reusing phosphogypsum in the road base by blending it with various different types of materials in order to determine the range of phosphogypsum stabilized road materials that meet Florida standard specifications for road and bridge construction. In this petition, Mosaic has proposed reusing phosphogypsum with an average radium-226 concentration of about 15 picocuries per gram, but up to 35 picocuries per gram to allow for some variability in between those phosphogypsum samples. Mosaic is also committed to extensive environmental and groundwater monitoring, again in order to prove that the reuse of phosphogypsum in this manner is at least as protective to human health in both the short and long term. And Mosaic has also proposed that their road base will only contain about 30 to 50% of raw phosphogypsum blended with 4 other types of materials. The small-scale pilot road itself will contain about 8 different sections, 4 of which are control sections with no phosphogypsum that then alternate in between 4 different test sections, where that phosphogypsum is blended with either lime rock recycled concrete aggregate, recycled asphalt pavement, or a mixture of sand and cement. And at this point, it's important to note that this actually isn't the only petition that has previously been approved by the EPA requesting to reuse phosphogypsum as a road construction material. In 2019, the Fertilizer Institute, also known as TFI, submitted a petition to the EPA requesting the reuse of phosphogypsum in government road construction projects. And although they did receive EPA approval in 2020, that approval was shortly withdrawn in 2021, not on the basis that there was fault found within either the petition or the dose and risk assessments, but rather because that approval was contingent on TFI providing stack-specific and phosphogypsum-specific information within a certain time period, and they just weren't able to meet that time period. But the reason why I mention this and why it's important to know is because Mosaic's petition relies heavily on that submitted by TFI, including their dose and risk assessments, to the point where they actually just incorporate TFI's petition by reference in their own. So in order for us to understand the petition submitted by Mosaic and approved by the EPA in 2024, we must also understand that submitted by TFI. And it was the small-scale pilot road study that led me to explore this area of research in the first place for my thesis and this presentation, because it didn't sound like the best idea to me at first, and I wanted to see if there were any holes that I could poke in either the petition or the research itself. And in order to do that, I developed the following two questions as goals to answer in this presentation, those being, are there any areas of research which maybe the EPA or Mosaic didn't or only briefly considered, which might impact the applicability of the results of the small-scale pilot road study for future nationwide implementation? And does the reuse of phosphogypsum in this manner truly eliminate T-norm concerns, such as those that we've already seen with the current methods of disposal, without creating a new additional or a new equivalent or worse T-norm issue down the line? And in order to answer these questions, the first thing that was done was a comparison of the dose and risk assessments performed by the EPA in their 1992 risk assessment, TFI in their 2019 petition, and Mosaic in their 2022 petition, starting with that road design. And although there were minor similarities and differences found in the proposed road designs between the EPA, TFI, and Mosaic, the one that's going to concern us the most is going to be where that phosphogypsum is going to be reused and what the average radium-226 concentration is going to be as a result of the incorporation of that raw phosphogypsum. Both the EPA and TFI proposed reusing phosphogypsum in both the road base and the road surface, while Mosaic only plans on incorporating phosphogypsum in the road base, mainly to provide an element of protection to that phosphogypsum stabilized road material from direct contact with either rain or surface water, as well as to provide additional shielding to members of the public. The EPA estimated that their road surface would contain on average about 4.5 picocuries per gram of radium-226 from that raw phosphogypsum, while TFI estimated that their road surface would only contain less than a picocurie per gram of radium-226, and both the EPA and TFI estimated that their road base would contain anywhere from 13 to 13.5 picocuries per gram of radium-226. Mosaic, on the other hand, had a little lower estimated average radium-226 concentrations, estimating anywhere from 4.5 to 7.5 picocuries per gram of radium-226 in their road base as well. And the differences in these average radium-226 concentrations can be attributed to multiple factors, including just different estimated average radium-226 concentrations from the raw phosphogypsum that they planned on using based on different stack sampling measurements, different weight percentages of phosphogypsum in that road surface layer, and then different incorporation percentages of phosphogypsum in the road base layer, with the EPA and TFI proposing that their road base would only contain about 33% of phosphogypsum blended with either clay, sand, or soil, while Mosaic again proposed that their road base could contain anywhere from 30 up to 50% raw phosphogypsum blended with either lime rock, recycled concrete aggregate, recycled asphalt pavement, or a mixture of sand and cement. Regarding the source terms that the EPA, TFI, and Mosaic included in their dose and risk assessments, they all use the same radionuclides, measurements, and calculations in order to determine the concentration of radionuclides present in that phosphogypsum in those road bases. And they all started by measuring the actual radium-226 concentration in their raw phosphogypsum samples, And once that actual measured radium-226 concentration was determined, they then calculated the uranium-238 concentration by using an activity ratio established by the EPA in 1992 in their risk assessment specifically for phosphogypsum samples. Once that uranium-238 concentration was determined, its decay products, thorium-234 and protactinium-234 metastable, were assumed to be in secular equilibrium with uranium-238, and then uranium-234 and thorium-230 were also calculated from that determined uranium-238 concentration by again using activity ratios established by the EPA in 1992 specifically for phosphogypsum samples. Lastly, all of the decay products of radium-226 were assumed to be in secular equilibrium with radium-226. And in between the EPA, TFI, and Mosaic, about 7 reasonable maximum exposure scenarios were developed in which members of the public might be exposed to that phosphogypsum contained within these road-based materials. And these would include a road construction worker who exclusively built phosphogypsum-based roads and wasn't afforded any shielding either by the road surface or any equipment, a truck driver who would drive phosphogypsum from the stacks to these construction sites and wasn't afforded any shielding by the cab of the truck, a utility worker who would be exposed to phosphogypsum in the road base while performing utility work and while also in a trench that had been dug out in the middle of these roads, road users who would routinely commute along these phosphogypsum-based roads, nearby residents who lived about 50 or more feet away from these phosphogypsum-based roads, a reclaimer scenario where a phosphogypsum-based road might be abandoned, destroyed, a home built on that land, and then someone live in that home for a certain period of time, and then an off-site individual who might live 100 or more feet away from a phosphogypsum-based road and be consuming food and water that might have been contaminated as a result of radionuclide leaching from these phosphogypsum-based roads into the groundwater pathway. And at this point, you might notice that not all of these scenarios were considered evenly by the EPA, TFI, and Mosaic, and this was mainly just due to the nature of Mosaic's small-scale pilot road study, that it was of reduced size, reduced duration, and primarily on privately owned land by Mosaic, meaning that the general public isn't going to have access to this small-scale pilot road. So certain scenarios like the utility worker, the reclaimer scenario, and the nearby resident just aren't going to be applicable. Mosaic also argued that road users weren't going to be applicable as well, again, because the general public doesn't have access to this road, but they did acknowledge that limited employee travel would occur, but any doses to these employees should be negligible. Lastly, regarding the offsite individual, because in 1992 the EPA determined that any dose to this individual would be negligible because they calculated that radionuclides shouldn't even reach the groundwater pathway for more than 10,000 years, this scenario wasn't included in either TFI's or Mosaic's petitions in 2019 or 2022, so we won't be talking about it further in this setting for now, so we're just going to table it, but it will come up later on in this presentation. In terms of total exposure durations, because the EPA only calculated annual doses to the members of the public in these reasonable maximum exposure scenarios, and because Mosaic only calculated doses for about a few weeks to a month, the annual doses calculated by the EPA and TFI were compared to one another and then multiplied by the total exposure durations proposed by TFI, mainly because those total exposure durations proposed in their petition were truly reflective of actual long-term use by the general public in a future nationwide implementation scenario. These total exposure durations would include about 5 years for road construction workers and truck drivers, 1 year for a utility worker, and then 26 years for road users, nearby residents, and reclaimer residents as well. And once these effective doses were estimated for those total exposure durations, they were then compared to the EPA's lifetime cancer risk level of about 3 in 10,000 additional fatal cancers, or an effective dose of about 600 millirem, with that dose to risk conversion being calculated by using a dose to risk coefficient established by the ICRP in publication 103, and all of these effective dose estimates would assume linear no-threshold dose models. In terms of the exposure pathways that would contribute to these effective dose estimates, they would include direct gamma exposure, dust inhalation, and accidental ingestion by a road construction worker, direct gamma exposure to a truck driver and a road user, direct gamma exposure and accidental inhalation and ingestion of dust to utility workers and nearby residents, and then direct gamma exposure, inhalation of radon, and ingestion of contaminated water and food by a reclaimer resident. And once all of these exposure pathways were considered and those total effective dose equivalents were estimated, the results of this largely showed that almost all of these reasonable maximum exposure scenarios were well below the EPA's lifetime cancer risk level of 600 millirem, with the exception of the EPA's estimated effective dose to a reclaimer resident for that total 26-year exposure duration, where they actually estimated an effective dose nearly 6 times their own cancer risk level at nearly 3.6 rem, while TFI only estimated an effective dose to a reclaimer resident for the same 26 years being about 78 millirem. And before I get into why these estimated effective doses were so different, you might notice that at this point, Mosaic's estimated effective doses were removed from these figures, and that's mainly just for ease of visualization. Because Mosaic, again, relied so heavily on the petition proposed by TFI, including their dose and risk assessments, their dose and risk assessments were just scaled down versions of TFI's dose and risk estimates. So including them here would be just duplicative of TFI's estimates on a smaller scale. So they were just removed for ease of visualization. But to get back to the differences in these estimated doses, the reason why they were so different between the EPA and TFI was mainly just due to different underlying assumptions, with TFI claiming that a reclaimer scenario in general was extremely hypothetical, citing multiple legal and institutional roadblocks which would make the scenario incredibly implausible, and TFI also claimed that multiple of the EPA's assumptions were extreme and resulted in unrealistic dose estimates. On the other hand, the EPA considered TFI's dose and risk assessments likely to be underestimates, citing some of their assumptions, like the fact that they assumed that a reclaimer resident would spend 100% of their time indoors for that total 26-year exposure duration, as well as an increased basement cover layer thickness, both of which would provide additional shielding to that reclaimer resident and reduce their effective dose, as well as the fact that TFI assumed radon diffusion coefficients for intact concrete for that basement layer, meaning that there would be reduced radon flux into the home and again, reduce that effective dose estimate. However, the EPA did acknowledge that TFI was able to demonstrate that dose and risk estimates could be within acceptable limits depending on how that home was constructed. So, in their 2020 approval letter to TFI, the EPA included a stipulation restricting the future abandonment of phosphogypsum-based roads in order to entirely eliminate any unacceptable risk to a member of the public. And although this stipulation wasn't included in the EPA's approval letter to Mosaic in 2024, this was mainly just due to the fact that, again, the reclaimer resident scenario wasn't considered applicable to Mosaic's small-scale pilot road study. And the EPA made sure to point out that the lack of inclusion of this stipulation didn't imply any conclusions about the risk to a reclaimer resident, and that they would again revisit this scenario for any subsequent petitions submitted outside of Mosaic-owned property. So ultimately, how did this comparison of dosing and risk assessments help us answer the question of whether or not the reuse of phosphogypsum in this manner truly eliminates T-norm concerns without creating new equivalent or worse T-norm issues down the line? Well, it was concluded that as long as the EPA continues to include this stipulation in future petitions, especially for nationwide implementation, any unacceptable risk to a member of the public can be entirely avoided. So now that we've established the fact that these phosphogypsum-based roads can be implemented in a manner that is protective to human health, other factors must be considered, such as site-specific environmental factors, weathering and erosion, and vehicular wear and tear, and whether or not they could potentially increase heavy metal and T-norm leaching into the local environment from these phosphogypsum-based road materials to a point of concern or exceeding permissible limits. And in order to do this, the petitions submitted by both Mosaic and TFI, as well as all of their supporting documents, were analyzed, and then a literature review of currently available literature was carried out using keywords related to any of those specific factors that we just mentioned. And the results of this literature review largely showed that there was significant evidence that little to no harm to the environment should be expected to occur as a result of the leaching of heavy metals or radionuclides from phosphogypsum-based road materials. starting with, again, the EPA's 1992 risk assessment, where they assessed that offsite individual and modeled radionuclide leaching from phosphogypsum-based roads to the groundwater pathway and determined that radionuclides weren't even calculated to reach that groundwater pathway for more than 10,000 years. In TFI's 2019 petition, they also included a screening analysis of heavy metal leaching and determined that it likely wasn't even a complete exposure pathway. And then in 2022, Mosaic also included extensive modeling of both heavy metal and radionuclide leaching from these phosphogypsum-based roads into the local environment and the groundwater pathway, where they determined that although initially some heavy metal concentrations would exceed groundwater cleanup target levels or drinking water standards in the state of Florida, in that leachate directly beneath that road base layer, by the time those heavy metals would reach the groundwater pathway, they would be diluted to a point of compliance by those underlying road base layers, as well as the underlying soil. Lastly, additional studies in 2020 and 2023 also demonstrated that a variety of phosphogypsum-based road materials demonstrated extremely high immobilization of heavy metals. And although some of these sources only talk about heavy metal immobilization and migration, because the leaching of heavy metals and radionuclides is known to be interrelated, these studies can still help provide valuable information and help us predict the behavior of radionuclides in future implementation scenarios. So again, the results of this literature review largely show that there should be no to little harm expected to the environment as a result of any heavy metal or radionuclide leaching. However, I did want to point out an assumption made by both TFI and Mosaic in their petitions regarding heavy metal and radionuclide leaching. That being that they assumed that the paving layer would provide complete isolation of phosphogypsum in the road base from direct contact with water, which, if these phosphogypsum-based road materials were to experience direct contact with water, that could lead to the increased migration of heavy metals and radionuclide leaching into the local environment. And although this assumption is certainly reflective of maybe a new or a freshly paved road, is this assumption going to be truly reflective of actual long-term performance and use by the general public, right? Is this going to be truly reflective of the impacts of weathering and erosion, as well as vehicular wear and tear, which might lead to fault formation, cracks, and potholes in that surface layer, which then might lead to direct contact with water and thus increased heavy metal and radionuclide leaching into the local environment? TFI did briefly consider the impacts of weathering and erosion and vehicular wear and tear in their 2019 petition when questioned by the EPA. And regarding weathering and erosion, TFI stated that because those heavy metal and radionuclide concentrations were calculated to be so well below permissible limits, that any impacts or increases to their concentrations in that groundwater pathway from weathering and erosion shouldn't lead to them then exceeding those permissible limits. Regarding vehicular wear and tear, TFI referred back to previous sources that stated as long as those phosphogypsum-based road materials were correctly optimized, they should actually require more minimal and more infrequent maintenance when compared with traditional road materials. However, other additional independent sources have pointed out that phosphogypsum-based roads can be susceptible to mutually reinforcing cycles of water absorption and thus fault formation, where water would absorb into these phosphogypsum-based road materials, leading to an increase in porosity, leading to deformation and cracking, which leads to an overall weakened resistance to water, causing more water absorption, and then that cycle repeating itself until the overall long-term performance and durability of these phosphogypsum-based roads could be broken up and significantly hindered. Lastly, another source pointed out that although Ukraine used to implement phosphogypsum-based roads, they have since ceased that implementation due to the unexpected short duration of these roads, as well as the potential of harm to the environment, both of which seem to directly contradict the conclusions made by TFI. All to say that, again, there is significant evidence that little to no harm to the environment should be expected to occur as a result of heavy metal or T-norm migration from these phosphogypsum-based roads. However, perhaps more consideration should be given to the impacts of weathering and erosion and vehicular wear and tear than has been given previously. Lastly, the final site-specific or environmental factor that I wanted to talk about today is the effect of salt water on the stability and durability of phosphogypsum-based roads. And this is mainly just because most of the literature and the studies that I found really only assessed the impacts of deionized or freshwater on stability and durability of phosphogypsum-based roads. And there were a few studies out of Louisiana State University in the early 2000s that assessed the impacts of saltwater on the stability of phosphogypsum-based composites for use in marine environments. And they found completely different reactions. They started off by blending phosphogypsum with either fly ash and cement or fly ash and lime, and then subjecting these composites to the same field submergence and dynamic leaching test, and they showed completely opposite reactions. With the phosphogypsum-based composites blended with cement experiencing a favorable reaction with that salt water, creating a high pH environment and precipitating what was essentially a protective calcite coating onto the surface of these composites. While the phosphogypsum-based composites blended with lime experienced the formation of internal hydration products, resulting in diametrical expansion of those composites that then neutralized any benefit a calcite coating could provide. This resulted in the phosphogypsum-based composites blended with cement maintaining their physical integrity for nearly 1.5 years, while the phosphogypsum-based composites blended with lime severely degraded within 15 weeks. And although phosphogypsum-based composites for use in marine environments are obviously very different from phosphogypsum-based road materials, perhaps some consideration should be given to the impacts of saltwater on phosphogypsum-based roads that might be implemented in coastal areas where they might experience routine annual submersion caused by hurricane or inclement weather seasons, such as the Florida coast. So ultimately, how did this review of site-specific environmental factors, weathering and erosion, and vehicular wear and tear help us determine if the reuse of phosphogypsum in this manner truly eliminates T-norm concerns without introducing new equivalent or worse T-norm issues down the line? Ultimately, it was concluded in agreement with TFI that it wasn't likely that the impacts of weathering and erosion or vehicular wear and tear could increase or amplify heavy metal or T-norm leaching to a point of exceeding permissible limits in the groundwater pathway. However, it was still considered a valuable area of research to explore and confirm, again, in order to prove that the reuse of phosphogypsum in this manner is truly at least as protective to human health in both the short and long term as storing it in stacks. But the same couldn't be said for the effects of saltwater on phosphogypsum durability and stability. And with predicted increases in inclement weather, as well as storm surge along the U.S. Gulf and Florida coast, consideration should be given to the effects of saltwater on phosphogypsum-based road materials to ensure that their durability will be maintained and T-norm or heavy metal leaching not enhanced in future nationwide implementation. Finally, now that we've asked the two most important questions, those being, can we implement phosphogypsum-based road materials in a manner which is protective to both human health as well as the environment, a more practical question had to be asked. That being, can we actually deplete all of the phosphogypsum that we currently have stored in the US by reusing phosphogypsum as a road-based material? And in order to answer this question, the U.S. Department of Transportation Federal Highway Administration Statistics Series was consulted for general information about the U.S. public road system because it provides reasonably accurate and current information about U.S. public roads every single year. And then the following equation was created in order to give a rough estimate of exactly how much phosphogypsum would be needed to replace all U.S. public roads based on the existing available mileage given by the Federal Highway Administration Statistics Series. Because the Federal Highway Administration breaks up U.S. public road systems by functional systems, which classify roads based on the role that they play in vehicular traffic, the number of lanes per functional system was then multiplied initially by the volume of the road base per lane per functional system, with information about, say, the width and the length of these functional systems gained from or taken from the Federal Highway Administration Statistics Series, while information such as the height or the thickness of that road base being taken from Mosaic's proposed road design, mainly because it's likely that any future nationwide implementation of phosphogypsum-based roads will be based on the results of Mosaic's small-scale pilot road study. Once that value was then determined, it was then multiplied by the range of densities of the phosphogypsum stabilized road materials that Mosaic proposed in their petition, as well as those incorporation percentages of phosphogypsum that Mosaic proposed as well. And once that amount of phosphogypsum was determined that could replace all existing public roads, In the US, it was then compared with the amount of phosphogypsum that we currently have stored, either in the US or in Florida, in order to determine the percentage and mileage of public roads that we could potentially replace or build across the US. And the results of this calculation show that out of the 4.2 million miles of public roads in the US, if we were to reuse the entirety of the US stockpile, that 1.7 billion tons of phosphogypsum, we would actually only be able to replace about 13 to 24% of existing road bases, meaning that we would need nearly 4.2 to 7.6 times the amount of phosphogypsum that we currently have stored in order to replace all roads across the US. So this calculation was able to demonstrate that we certainly have more than enough existing roads to use up all of our currently stored phosphogypsum, as well as any future accumulation. However, because Florida disproportionately stores the majority of phosphogypsum in the US, holding one of the 1.7 billion tons of phosphogypsum across the country, if Florida were to replace every single road in their own state, they would actually only be able to use about 22 to 40% of those 1 billion tons of phosphogypsum that they have stored, meaning that other neighboring states such as Alabama, Georgia, Mississippi, North Carolina, and South Carolina might have to accommodate Florida's phosphogypsum into their own roads in order to reuse all of Florida's phosphogypsum. So ultimately, how did this calculation help us answer the question of, were there any areas of research which maybe Mosaic or the EPA didn't consider, which might impact future nationwide implementation? And the following two questions were developed as answers to this question. Those being, although there are clearly more than enough existing miles of roads in the US public road system to reuse all current and future storage of phosphogypsum, would neighboring states even be willing to accommodate Florida's phosphogypsum into their own roads? And if not, what happens to the excess phosphogypsum then? And more importantly, how often do these road bases need to be replaced with phosphogypsum stabilized road materials? And then what happens to that phosphogypsum stabilized road material once it reaches the end of its life cycle? And the reason why this is so important to ask is because radium-226 has a half-life of about 1,600 years, meaning that it's going to far outlive the lifetime of any of these road-based materials. So if it's improperly disposed of, say in a landfill, or recycled in an indoor recycling facility where there might be a buildup of radon indoors, this could potentially lead to an unacceptable risk to a member of the public if it's not considered prior to future nationwide implementation. So ultimately, what were the considerations or conclusions that were made in hopes that they might be considered by the EPA or petitions for future nationwide implementation in order to ensure that the reuse of phosphogypsum in this manner is at least as protective to human health as storing it in stacks? Ultimately, the following three considerations were made, those being that the EPA should continue to include that stipulation restricting the future abandonment of phosphogypsum-based roads in order to entirely eliminate any unacceptable risk to a member of the public, that further consideration should be given to the impacts of saltwater submersion on phosphogypsum-based road stability in coastal areas to ensure that their durability will be maintained and that T-norm leaching not enhanced in future implementation nationwide. That consideration should be given to how the disproportionate storage of phosphogypsum in Florida will be depleted and how old phosphogypsum in road bases will be either recycled or disposed of at the end of their lifetime in order to, again, prevent unacceptable risk to a member of the public as a result of the T-norm contained within phosphogypsum. And finally, what should you take away from this presentation? Well, with more than enough public roads across the US to deplete phosphogypsum stacks, the implementation of these phosphogypsum-based road materials, which can be protective to public health and the environment in both the short and long term, has largely been demonstrated. And with consideration of some of the questions and areas of concern proposed in this presentation, the implementation of phosphogypsum in road materials could represent a promising turning point in phosphogypsum disposal and the possibility of a new era of roads in the US. Thank you for listening, and at this point, I would be more than happy to take any questions.